Start recording. Okay, so quickly recall some basic definitions and constructions. So a path in X is called a loop if it starts and ends at the same point, right? It's called a loop based at x0 if it starts at x0 and ends at x0. And the set of path homotopy classes of loops based at x0 with operation given by concatenating loops, or more precisely by multiplying homotopy classes of loops, forms a group called the fundamental group of X at x0, and it's denoted by pi1 of X, comma, x0. Okay, so, and it's called the fundamental group of X at x0. It has, since it's a group, it has an identity element, and that identity element is the homotopy class of the constant path at the base point. And inverses are given by running a path backwards. Okay. So our first example is that or first computation is that the fundamental group of Euclidean space based on any point x0 is the trivial group, right? It consists of a single element, the homotopy class of the constant loop at x0, right? In other words, this is equivalent to saying that any loop in Euclidean space based at x0 is homotopic to the constant loop at x0. So any loop can be shrunk to the constant loop in Euclidean space. And this is clear since we can use a straight line homotopy, right? We can just follow these lines. All straight line segments from points in the loop to the constant loop, right? You just follow those lines and play this movie that starts with the loop and ends with the constant loop, parameterized by the interval from 0 to 1, right? The unit interval. And that gives you a homotopy for any loop, right? So any loop is homotopic to the constant loop in Rn. So there's only one class, the class of the trivial element, the identity. And this argument works for any convex set in Rn, right? Because if I'm using straight lines, then the homotopy will stay inside that convex set, and we'll define a homotopy of a loop inside a convex set to a constant loop, right? So now you may ask, to what extent does pi1 of X at x0 depend on the choice of the base point? And the answer is that, well, if you have a path, let's call that alpha, from x0 to x1, then that path defines a homomorphism of groups, which I'm going to call alpha hat, which is given by conjugating a loop with the path alpha. So I should start using Greek letters for paths and loops. So I'm going to erase this F here. And I'm going to use gamma, maybe, because I will use F and G's for maps later. So this is what I mean by conjugating, right? You take the homotopy class of a loop and you multiply by the inverse of alpha on the left and alpha on the right. Right, so what's the picture? You have a loop here like that, and you have a path alpha. And conjugating by alpha, you obtain a new loop, but now it's based at x1. right? You do alpha inverse, then you do the loop gamma, and then you do alpha. And you get a loop based on x1, right? So given any path, we can change the base points of the loops through these like whisks, right? And I claim that any path gives an isomorphism between fundamental groups, namely A hat is a group isomorphism. This map is a group isomorphism between that and that. So that's a claim. So can anyone tell me what the inverse would be?
Like the inverse loop of the conjugation? The inverse of what?
The inverse of this isomorphism is given by what?
It'd go like alpha, gamma, alpha inverse, alpha bar.
Yeah, that's correct. So that's basically saying what? Basically saying the inverse is given by the inverse of alpha hat, right? You'll get the formula you just said if I do that. That would be a map going like that, right? Because alpha inverse if a path is a path from x1 to x0. So this is what I mean. So, first we show alpha hat is a homomorphism. It's compatible with the multiplication. That's kind of straightforward, right? But let's just show it. If you take alpha hat of f and you take alpha hat of g, so again, I should use Greek letters for these loops, but I will not do it here. Then by definition, alpha hat of f is given by that conjugation, and alpha hat of g is given by that conjugation. But now star is associative, right? So I can just forget about these parentheses because it's associative, right? So I can just multiply in whatever order I want. And I get that these and these cancel. They give you the identity because this is the inverse of alpha in this group, right? So that cancels. And I get that. But this is exactly conjugating f star g with alpha, which is that. So we just showed that alpha hat is a homomorphism of groups. It's compatible with the multiplication. And now we show that it's an isomorphism. So I'll just say, well, let's go through it. The inverse of alpha hat is given by beta hat, where beta is the inverse of alpha. Okay, I just don't want to write like that looks like, I don't know, like a little house or something. So beta hat, where beta is the inverse of alpha, is the inverse homomorphism of alpha hat, and that's clear, right? So you just compute it. So what's beta hat? So it's given by that. But since beta is the inverse of alpha, the inverse of beta is just alpha, right? This would be, well, I would write it like that, right? That's just alpha, right? So that's just alpha. This is alpha bar. So this is what Sophia said, right? Conjugating the other way. So that's what beta does. And then when I compose with alpha, so I conjugate in this way, then I conjugate the other way. So these cancel, and I get H back, for example, right? So the composition of these two is the identity. Similarly, the other composition will give you the identity. So this will define the inverse homomorphism, and thus alpha hat is an isomorphism of groups. Okay, so any path gives you an isomorphism of fundamental groups at different base points, right? A priori, the fundamental group depends on the base point, but I'm just saying that any path between 2 points gives you an isomorphism between fundamental groups at those points, right? Of course, this Isomorphism is not unique. It's not canonical. It involves a choice of path, right? But that's fine. It actually involves a choice of homotopy class of path, right? Any two homotopy paths will give rise to the same isomorphism, since we're only using the homotopy class of the path alpha. A corollary, if any two points are connected by a path, namely if x is path connected and x0 and x1 are 2 points in X, then the fundamental groups at those points are isomorphic. By this symbol, I will denote, I will mean isomorphism of groups, okay? Or homeomorphism of spaces as well, okay? So the isomorphism class of the fundamental group is well defined, independent of the base point, associated to any path-connected space, right? The isomorphism class. Any questions? Does this make sense to everyone? So a remark, if X is not path connected, then if C is one of the path, independently of X is not path connected, maybe C is all of X. So let me just say it in this precise way. If C is a path component of X, such that X0 lies inside C, then the fundamental group of C at X0 is the same as the fundamental group of X at X0, right? Because all paths will stay in the path component, right? Paths cannot leave to a different path component by definition, right? But of course, we will restrict our attention to path-connected spaces, because if not, you can work component by component, okay? Another remark is that the fundamental group is not non-abelian in general. There's no reason why this, in general, and in many cases it will be abelian, but there's no reason a priori why the star operation is commutative, right? If I do a alpha and then beta, there's no reason why that's the same as doing beta first and then alpha. Okay, of course, we haven't computed any examples yet, but we will see. We will see. As soon as you have pictures like that, like if you have a space like that, like a figure 8, like a graph with 2 loops, as soon as you have that, then you have a non-abelian fundamental group. Okay, we will see. But for example, the fundamental group of the circle will be the integers, which is abelian. We'll prove that on Friday probably. Okay. Yeah. So far we haven't computed any explicit examples of the fundamental group. Only the fundamental group of convex sets in Euclidean space that we showed it's trivial, right? When we have this, when we have a trivial fundamental group, we say a space is simply connected, right? So more precisely, a space is simply connected if it's path connected and if the fundamental group at any point x0 and hence at every point x0 is the trivial group, right? And we write it in this way. We write pi1 of x equals 0 whenever we want to say the fundamental group is trivial. Okay, we mean this is the trivial group. This is the group with one element. You've probably seen this condition in Calc 2, multivariable calculus, or in complex analysis, right? So simply connectedness. If you haven't seen it before, that's fine. So a lemma, if x is simply connected, then any two paths in x having the same and initial final points are path homotopic. So simply connectedness is saying that every loop is contractible. And I'm saying that implies that any two paths starting and ending at the same point are path homotopic, right? So what's the proof? So the idea is you look at the paths, two paths, let's say alpha and beta, that start and end at the same point, right? And then you consider a loop, the loop formed by these paths. Namely, you look at alpha, then followed by the inverse of beta. That's a loop at x0, right? And that means that since your space is simply connected, that means that that loop is contractible. You can contract it to the constant path at x0, right? So this is what this means. So that loop given by doing alpha and then the inverse of beta is path homotopic to the constant loop. That's what it means for a space to be, that's a consequence of the space being contractible. So that means that if I do this loop followed by beta, well, that's the same as just doing alpha because these two will cancel, right? Beta and beta inverse. But on the other hand, this is the same as doing the constant loop at x0 because this is a constant loop at x0 by simple connectivity followed by beta, right? And this is the same as beta. So that implies that these two classes are the same. So in any simply connected topological space, any two paths are homotopic. Any two paths with the same initial and same final point are path homotopic. Does that make sense so far? Everything? Great.
I have a question.
Yeah.
So if you can do that, then necessarily, like we mentioned how like if it's a convex set, it'll be the trivial, like its fundamental group will be the trivial group. Is that true for simply connected things? Simply connected spaces? Like will its fundamental group be trivial?
By definition. I mean, space like simply connected if it's path connected and the fundamental group is trivial. I'm just saying that if this holds, then it follows that any two paths are homotopic. I'm not saying anything about convexity or convex sets or anything. This is for an arbitrary topological space. All right. Convexity, just I'm not sure it makes sense for any topological space. It's just for like where you have a notion of straight line paths, like in Rn and so on. So this, I'm just saying, just defining what simply connectedness is, and I'm just explaining a simple consequence of simple connectivity.
Yeah, I suppose I'm fine with that. I guess I don't know why you're talking about contractibility.
Because what does this mean? That the fundamental group is a trivial group. It means that any loop is contractible. This phrase, any loop is contractible, means any loop is homotopic to the constant loop. I'm just using different words to mean this, right? So the fundamental group being trivial, this being trivial, means that this is there's only one class, namely the class of the constant loop, right? So any loop here, this is the set of homotopic classes of loops, right? So that means that any loop, there's only one class, right? So any loop is homotopic to the constant loop.
Is that the same as saying the identity is null homotopic?
No, that means any loop is null homotopic. Null homotopic means, well, depends how I didn't define this word.
Yeah,
so
you did, I think.
Not use it. Yeah. I just mean homotopic to the constant loop. Any loop is homotopic to the constant loop.
Okay, then the exercise I'm looking at is defining it differently.
I will use the words contractible. Any loop is contractible. That means the same as any loop is homotopic to the constant loop. Is that clear? Is it clear what it means for the fundamental group to be trivial? Why that implies that any loop is homotopic to the constant loop? Any questions? All questions are good, always. Okay, I'll continue. Right, so we want to say that the fundamental group is a topological invariant of a space. What does that mean? We want to say that if we have two homeomorphic spaces, then their fundamental groups are isomorphic. Okay, so in order to say this precisely, I have to introduce some definitions and some notation. So the first definition is that of an induced map at the level of fundamental groups. So if you have a continuous map between spaces with base points, so what does that mean? I'm using this notation, but that just means that H is a continuous map from X to Y that maps X0 to Y0. Is that clear? I'm just going to write it like that. X is a map from X to Y that maps X0 to Y0. Okay, so this is just notation to denote this. Or we also call these maps of pointed spaces. A continuous map of pointed spaces. A pointed space is just a space with a base point. Okay. So suppose we have a continuous pointed map or a continuous map of pointed spaces like that. Then I'm going to define H star, or also in the literature, you might find it denoted by pi1 of H, okay, to be a group homomorphism from the fundamental group of X at X0 to the fundamental group of Y at Y0. And it's just defined by, at any loop gamma, at the homotopy class of a loop gamma, it's just defined by taking the homotopy class of the loop in Y given by the composition of gamma and H, right? Gamma is a map. So gamma is a map. I should do it like this. Gamma is a map from the interval to X, right? And H is a map from X to Y. So I can just compose this to obtain a loop in Y. Right? So given any loop, any homotopy class of loop, I get, by composition, I get the homotopy class of a loop in Y. Is this definition clear? It's called the induced map, the map induced by H on fundamental groups. So any continuous map of spaces induces a map of fundamental groups. Of course, there's something to check. H star is well defined, right? Because I'm defining it using representatives of a homotopy class, right? So I have to check that if I vary this representative, but staying in the same class, namely if I vary the loop gamma by a homotopy, or if I use a homotopic loop gamma prime, then I get a homotopic loop here, namely H composed with gamma prime will be homotopic to H composed with gamma. But that's clear, right? Because if gamma is let's say path homotopic to gamma prime, then H of gamma is homotopic to H of gamma prime, path homotopic. So if I use a homotopy here, let's say capital H, then the homotopy here will be given by H composed with capital H, right? Recall a homotopy of paths is just a map of the square to X, right? So I can compose that with H. It's little h. Okay. So that first claim is straightforward. I just wrote it here. Yeah, sorry. Didn't see that. So it's written down here. This is what I just said. And then the second claim is that this is a homomorphism of groups. That's also straightforward once you convince yourself that the composition of H, if you multiply the composition of H and alpha with the composition of H and beta, that's the same as multiplying alpha and beta and then applying H and then composing with H. So once you convince yourself of this, again, which is straightforward, you can quickly see that that implies that H star is a homomorphism of groups. It's compatible with the multiplication of loops. Okay, so any map of spaces induces a map of groups. That's what you have to remember or understand, right? Every map of spaces induces a map of groups.
So this is, then the induced map is going to be a functor from the category of topological spaces to groups.
Yeah, and if you know about categories and functors, it's okay if you don't. That's fine. But let me say some words. This, what I just said, is saying that pi1 is a functor from the category of pointed spaces, right? Because I've defined pi1 to be pointed. So category of pointed spaces to groups. So there's a language that in which you can say that abstracts what's going on here. It's called category theory. Okay, and in that language, this this says that pi1 is a functor, namely for any space you have a group. For any pointed space, you have a group, and for any map between spaces, you have a map between groups. That's what it means to be a functor. Yeah. Oh, and actually, I'm missing something in order to say that's a functor, which is that this is compatible with compositions, right? If you compose map of topological spaces, then that goes to the composition of maps between groups, and that's the next claim. So not yet. You need this claim in order to say that this construction pi1 is that of a functor. Okay, so this claim says that if you have two composable maps between spaces, namely if you have a map from X to Y, between pointed spaces, I mean, and the map from Y to Z, which is pointed, namely it takes the base point to the base point and that base point to the other base point, right? So if you have two continuous maps of spaces, then the induced map of the composition K and of K and H is the composition of the induced maps. And the identity map, if you have the identity map from a space to itself, then the induced map is exactly the identity map between groups. Checking these is completely straightforward, right? For example, what does this mean? By definition of this induced map, this means that this is the homotopy class of the loop gamma obtained by, this is the homotopy class obtained by composing the loop gamma with this map. But this is the same as, right? K star of H composed with gamma, which is the same as that, right? You first do that and then do that. So that shows that that is the same as that. And this is a triviality as well. Now this means that, yeah, all these claims, we can imply that pi1 is what is called a functor. There's a language that you see this situation repeatedly in different contexts of mathematics, and there's a language that works for all of these contexts, which is called category theory, but it's not needed for this course. Okay.
Then we also just show that it's a covariant functor also?
Yeah. Covariant functor means that the directions of the arrows, the direction of the maps are preserved, right? If you go from X to Y here, then you will go from pi1 of X to pi1 of Y, right? There are other kinds of functors that reverse the direction of the maps, and they have a different name. Okay. Anyway, those are just words right? There's kind of like no content. So corollary of the above claims is that if you have a homeomorphism between spaces, let's call that H between X and Y, then the induced map at the level of fundamental groups is an isomorphism. So in fact, the fundamental group is a topological invariant, right? Homeomorphism induces an isomorphism. So any two homeomorphic spaces have isomorphic fundamental groups. So why is that? Well, if you have a homeomorphism of spaces, then you have an inverse. Let's call that inverse K. What does it mean that K is an inverse of H? It means that K is a continuous map such that this is the identity, and also the other composition is the identity as well, the other identity. So this would be the identity on X, and this would, we lost it. You know, both compositions of X and of K and H are the identity. That's what it means for K to be an inverse, right? And every homomorphic, by definition, if H is a homomorphism, there's a continuous inverse. So I can just compose them. I claim that the induced maps are inverse to each other, the maps at the level of groups. And therefore they induce an isomorphism between groups, right? So how do I check that they're inverse to each other? So I check, I look at their composition of the induced maps. By the previous claim, that's exactly the induced map of the composition. But I know that this is the identity. And I know that the induced map of the identity is the identity map between groups. So I just check that the composition of the induced maps is the identity. And similarly for the other composition, it's the other identity. So this shows that H is an isomorphism of groups. So the fundamental group is a topological invariant. And as I said at the beginning of this chapter, it will turn out to be an invariant of a weaker notion of equivalence called homotopy equivalence. Okay, it's weaker than saying homomorphisms, but we will get there. Okay, for now, it's an invariant with respect to homeomorphisms.
So I think I maybe lost thread on where simply connected was coming into play for all this.
Yeah, it was just a definition, a random definition I made in the middle of the discussion.
Right. Why did we need it? What do we use it for?
We don't use it. I just said it's a separate discussion. I just said, oh, if a space has trivial fundamental group, then we say it's simply connected. And then I said what that implies. But this is,
it might be useful later when we talk about like if two spaces are homeomorphic, will their fundamental groups like necessarily be the same or like be isomorphic, right? Because you're going to talk about homotopy equivalence, and I think there's cases where there's like spaces that are homeomorphic but don't have the same fundamental group or something like that.
no, the spaces, homeomorphic spaces have isomorphic fundamental groups.
Well, then it's like the homotopy equivalence, right? The weaker one where like they might not have the same thing one place, but
No, not yet.
Okay.
Two homotopy equivalent spaces will have isomorphic fundamental groups as well. You want to say the converse direction, right? If two spaces have isomorphic fundamental groups, then they might not be, first, they might not be homeomorphic.
Yeah, I can't remember the implication, but whatever the implication is, I think that's why you're talking about the simply connected thing.
Yeah. Yeah, for now, I'm just making a definition. So I'm not using this definition so far. I'm just saying spaces which have trivial fundamental group are called simply connected. Period. Right? So let me say something. So I think I will not start a new discussion now. So I will leave this for Friday. So maybe we can just kind of, for the next 5 or 6 minutes, relax and talk more about what I just said. So first of all, let me notes. Let me remark based on what Sophia was saying. So if pi1 of x0 is isomorphic to pi1 of y, y0, or maybe I should say this does not imply x is homeomorphic to y. Okay. I mean, we have a counterexample, right? Can anyone tell me a counterexample that we have proven so far using what I have just mentioned? So what's a counterexample?
R and R2?
Yeah, good. R and R2, right? We know these are not homeomorphic, right? Oh, maybe this is what you were saying, Sophia, but now you can say they are both simply connected, but they are not homomorphic. Yeah, but you can say they both have isomorphic fundamental groups, but they are not homomorphic.
I can't remember if they will be homotopic equivalent
Yeah,
spaces.
they will. Yeah.
Okay.
Because both of these will be homotopy equivalent to a point. So it's harder to construct examples of non-homotopy equivalent. Of spaces with the same fundamental group, which are non-homotopy equivalent. That's a harder task, but doable.
So here's a question. Why are we using pi sub 1? Like, surely there's like a reason behind that there's a pi sub 2 somewhere, or is that something that's going to be relevant to us eventually?
Yeah, maybe not in this course, but there are other things called, maybe we can talk about that a little bit. How do I add a page? So why are we using pi1? So there are other groups you can associate to a space.
Are you asking why pi? Because it's like, it looks like a projection map.
I thought he was asking.
Yeah, I'm more asking about the subscript.
Yeah.
Rather than
Okay.
The one. Yeah, there's no reason why we're using pi, I guess. Guess is historical. P for Poincaré, maybe. Poincaré was the first person who introduced this construction. So for every non-negative number, you can associate you can associate a group to a space defined in a similar way. So instead of looking at, so here you look at homotopy classes of loops, right? Inside X. So these are the same as maps of a pointed circle to X, right? Of course, I was describing it like that. Maps from the interval that map the starting point and the end point to the same point, but that's the same as maps from the circle that map the base point of the circle to the base point here, right? So I can just think of this as maps from the circle to your space, based maps that preserve the base points, right? So here, I can look at maps from the pointed sphere to your space, homotopy classes of maps, right? Which take this base point to the base point. And then I can define a product operation as well for spheres. Okay? Generalizing the concatenation of loops. There's a way of making sense of what I mean by concatenate spheres. And here I take this 3-sphere, which of course I can draw. And I look at homotopy classes of maps like that. And I take the 4-sphere and then take, and so on, right? So what? So these are called the homotopy groups of a space. These are homotopy groups. If you know all of them, you still don't know your space up to homotopy equivalence, but you're close. I mean, you're closer, I guess. It has more information.
You said you can do this for every integer, but is there a point where like they all start being the same or something?
No.
Okay.
I mean, there is certain, for certain spaces, there's certain stabilization phenomena people study, but that's something else. But these are very complicated. Very, very complicated. Very hard to compute. It's kind of a major research area in topology, and it has been like that for the last 50 years. Computing, in particular, computing homotopy groups of spheres. Even these are very hard to compute.
Where your space is just a point?
When your
what
space
you're
is a
saying?
point, all of these are trivial. Yeah. Yeah. But for example, there are funny things that happen, which this was discovered by Hoff, that, for example, you can have this, you can look at the 2-sphere and you can look at the 3rd fundamental group, and this will not be trivial. There are non-trivial ways to map a 3-sphere into a 2-sphere. So this is non-trivial. But this you can compute.
Hoffman, like which Hoff? I'm sorry.
Hoff.
Oh, okay.
Heinz Hoff, maybe? Is that the name? Does anyone know? I think so. Hoff. From 19th century. Not 19th or yeah, 19th century. Yeah. Anyway, these are very interesting, and they contain a lot of information about your spaces, how they behave, and yeah.
I have a quick silly question, and I think I'm not sure you might have the answer to this, but why are we denoting inverse loops by a bar and not like
But
-1?
because why is that? There's no good reason for that,
Okay.
but because it's just I see, because this, yeah, I know why. This is not equal to the constant loop. Let's say B is a loop at x0. This is not equal to the constant loop. It's homotopic to the constant loop. So if we wrote it in this way, it would kind of suggest, I mean, it doesn't have to suggest that, right? But it would kind of suggest that this is an inverse, a strict inverse. That this is equal to the constant loop if I multiply them like that. But that's not true, right? It's not exactly the constant loop, right? If I do a loop and I go back, that's not exactly a constant loop. That's another thing, but it's homotopic to the constant loop, right? You can always like do like that and then keep going, do it shorter and so on, right?
Okay, so it's just more misleading even though it's the inverse element.
It's the inverse element at the level of homotopy classes. So this
Yeah,
is,
like with a bracket around it,
yeah,
right?
this is true. Then this hat is something that makes sense for a loop, not a homotopy class, right? You just reverse the loop. You go backwards.
You mean bar, right?
Bar, bar, bar. Bar. So you could say this. This is a true equation, I guess. Right?
Yeah, I don't know what inverse on the outside means.
Yeah, it just means the inverse of this element considered as a class. But since it's a bit confusing, we just, yeah.
Okay, that's fine.
Okay. Okay.